theta y. V m theta y. Now, can anyone want to tell me what's my boundary condition, please? Is it the same or different? And if it's different, what is it?
Wouldn't y be 0 on both?
Yes, y is equal to 0, but y is not helping us down here. Right? We have not integrated until y yet, so it's not going to help us, right? We only integrate the first time, we get shear force. Integrate the second time, we get bending moment. So what is our boundary condition for V and M, please?
Zero.
What is 0? 0 is correct, but what is 0?
The V and the M.
Huh?
The V and the M.
No, the V and M, the V cannot be equal to 0 because they are reaction.
Oh.
Right? This one can be equal to 0 because there's no support over here. Yes or no?
Yeah.
Right? So the only thing now is these two are equal to what? 0. Right? If you remove the, if I were to take out the support over here, right? What will happen to this entire structure? This entire structure will swing over. Yes or no?
Yeah.
Right? When that's the case, this is because moment is equal to what? 0. If I were to remove this support and keep this support over here, right? And we were to keep the roller, right? When we keep the roller, what will happen? The entire structure, if we were to keep here, the entire structure will swing this way. Why? Because moment is equal to what? 0. The only way that it will not swing is because it's built in. When it's built in, M is not equal to what? 0. That's why in a cantilever beam, it stays down there. It's not rotating because you have a counter moment that's reacting. So the free body diagram for this case is you have a vertical force at V at a distance 6, and you have a counter moment M6. That's why it's not equal to 0. Yes or no?
Yeah.
Okay. That's why this topic is not. You guys know all this. Okay. You guys know all this. Now the thing is how to put it mathematically. Yeah, how to put it mathematically.
Wouldn't the V be RA and the V
Yeah.
be RB?
Yeah, but you don't know yet. If you don't know, you cannot say it's equal to 0.
Okay.
Only boundary condition, the boundary condition, you have to know the exact value even before the analysis. Okay? Right. So that is the strength of the integration method. And what I've just shown you, if the support changes, the boundary condition change. Yes or no? Right. So let's solve for this one. Let's solve for this one. Okay. I'm interested now. So we go for, so let's solve for this one. So we know that dv over dx is equal to minus omega as a function of x. Right. So this is equal to minus 2000 x minus by what? 6000. 2000 x squared. Sorry. Minus 2000. Sorry. Minus by 6000. So we still write this. Am I right? So the next thing that we do, right, we integrate. So we integrate. So v as a function of x now, right? V as a function of, so this is equal to minus 2000 x squared over 2 minus by 6000 x plus by c1. Okay, so you have 1 minus 1000 x squared minus by 6000 x plus by c1. So this is my equation number 1, for example. So by looking at, did I do everything correctly? Yes, I did. Okay. So by looking at this now, can you find C1?
Yes.
No, you cannot find C1.
C1.
No, you cannot find C1 at all. Why you cannot find C1? Because you don't have any boundary condition down here. You don't know what they are. Okay, you don't know what is V at x equal to 0. You don't know what V when x is equal to what? 6. Okay, so the next thing we do is what? We let this whole expression be equal to what? Be equal to dm by dx. And this is still our equation number 1. Okay, so now m as a function of x now. Now, so this is going to minus 1000 x cubed over 3 minus by 6,000 x squared over 2 plus by C1x plus by C2. Okay, so now this will become minus 1,000 x cubed over 3. If I make mistake, you tell me, okay? Minus by 3,000 x squared plus by C1x plus by C2. This is our equation. Now, then we can start using our boundary condition. Yes or no? So our first boundary condition is when x is equal to 0, m is equal to 0. So we're going to substitute when x is equal to 0 and m is equal to 0 into equation number 2. So we like this, right? When they're all zeros, everything is so. Therefore, C2 is equal to what? 0. Then we write out m as a function of x is equal to minus 1,000, right? X cubed over 3 minus by 3,000 x squared plus by C1x. So this is your equation 2a now. So the next one we're going to substitute when x is equal to 6, right? M is equal to 0, right? Over here, when x is equal to 6, m is equal to 0, right? Into equation 2a. Right? So we have 0 over here equal to minus 1,000 6 cubed over 3 minus by 3,000, right? X squared, 6 squared plus by C1 multiplied by 6. So this will be equal to, so 6 power of 3, 6 power of 3 divided by 3 times by 1,000. So it's equal to minus 72,000 minus by 6 times 6 times by 3,000 is equal to 108 times 10 to the power 3 plus by C16. So C1 is equal to 72123 plus by 108 power 3 divided by 6 is equal to 30,000. I'll do it again, okay? So 6 power 3 times by 1,000 divided by 3 plus by 3,000 times 6 squared divided by 6 is equal to 30,000. So now the equation will become m as a function of x is equal to minus 1,000, right? X cubed over 3 minus by 3,000 x squared plus by 30 times 10 to the power 3. Okay, and then when that's the case, you also know what is v as a function of x now. So v as a function of x, right? So I'm going to copy this. So v as a function of x, because we know C1 undo. So this will be equal to v as a function of x is equal to minus 1,000 x squared minus by 6,000 x plus by what? Plus by 30 times 10 to the power 3. So mathematically, the function changes already. Okay, as you can see, it's not the same as what we have before. It's not the same, right? This is because our boundary condition what? Our boundary condition changes. So I really hope that you guys will embrace this technique, right? By changing the boundary condition, right? By changing the boundary condition, your equation changes already. Okay. So no doubt our initial function is still the same, right? Our omega is a function of x. Omega a function of x is still the what? It's still the same. Okay. So that is the integration method. Okay. Now, next, we're going to go into the deflection of the beam using the elastic curve. Okay, so anyone, any question, please? Anyone? Are you all clear? Or it's just, yeah, sorry, stupid question. Anyone have question? It's ridiculous to ask me everything clear. Okay, you need time to absorb
What does the theta mean again?
I'm coming into that next.
Okay.
Okay, right. So that is the integration method. And if I have time, okay, I can do 2 more examples. But I want to show you all the integration method first. I'm sorry, the deflection.
Eugene, there's
Yes.
a question in chat.
Could you explain the moment boundary one more time? Okay. So let's look at the moment boundary. So if this is our beam, thank you for telling me, okay? And this is our point A. And this is our point B. Right? So if we look at x is equal to 0, and we call this x is equal to L. If we look at VMM, right? So we know that V over here is not equal to 0. Because you have a reaction at point A, and you have a reaction at point B. It's not equal to 0. But the moment is equal to what? 0. Why? Okay. So now, let's say we were to remove B. Right? Remove B support. Right? Point A is still there. What will happen to the structure? Anyone? What will happen to the structure? Anyone? Someone say that I missed the 3000 somewhere. Oh yeah, he's right. C1X. Thank you. Okay. Brown. Thank you. Anyone? What will happen? The structure will rotate. Yes or no? Right? The structure will rotate. Right? You can see the structure will swing over. Right? That is why moment is equal to 0. Right? So what if now I were to remove my support at A, right? And this one I will keep. What will happen now? Now the structure will rotate the other way. Right? The fact that the structure will rotate means moment is equal to what? 0. Now, if we were to look at a cantilever beam now, so we know that a cantilever beam is fixed, right? It's fixed at one end. So this is point A, this is point B, right? So now I'll call this x is equal to 0. This one is x is equal to L, V, and M, V, M, M now. Now, can point A move? Can point A move? Right? Can it move? Right? If you have a load, if you have any load, can point A move? The answer is yes. So if it's yes, this will be equal to what? 0. Right? At point B, right? At point B, can point B move? Point B cannot move at all. So this is not equal to 0. Right? So now, if we were to remove point B, okay, remove support at point B, right? What will happen to the structure? The structure will rotate, right? Will swing this way. So when it can swing, the moment is equal to what? 0. Now, what if now we remove the support at point A? Even, in fact, there's no support, okay? If we remove support at point A, what will happen? Nothing will happen. It will not even swing. So that's where the moment over here is not equal to 0. Is that clear? Okay, I hope. Does that make sense? Is that what you want to know? Okay, good. Right. So now, the next thing that we're going to go for, I hope that is clear for every one of you. Okay. So the next one that we're going to go for, okay, we are going to look at deflection of beams. Okay, we're going to look at deflection of beam. Okay, using the elastic curve method. Okay. So again, our